video we are going to talk about the Gaussian elimination method and the backward substitution using Octave. So I open my Octave package. So first of all you have to define your coefficient matrix. So this is your coefficient matrix of the system, and this is your right hand side, right hand side. And I update A, I consider both coefficient matrix with the right hand side, so which is called augmented matrix, right? Okay, now I find the number of rows and number of columns. So n would be the number of rows, that means number of equations in this system, and number of rows including the right hand side. Here m is the number of rows, number of columns including the right hand side. Here I updated matrix A. Here A is an augmented matrix here, right? So here n is the number of rows and m is the number of columns with the right hand side, and okay, n is the number of equations, and this is a number of number of variables plus 1, because we include right hand side of those equations. So look at this. This is our matrix A is this one, and the variable matrix is X, and this is our B, right hand side. So I consider both A and B together, then I just ignore the variable vector here, right? So I consider both A and right hand side of these equation. Then my m would be here with this row, right, including this row. So j goes from how many rows, how many columns are there? 1 2 3, and number of columns of matrix A with this right hand side B, right? And here how many rows? Here there are, so let's say we have n number of equations, so we have n number of rows, right? This matrix is, so this is the dimension of this is the number of rows of matrix A with this row, right? So m would be number of rows of a number of columns of A plus 1. Okay, n is the number of equations. So I took two counters. One is for counter for columns, and j is for counting rows, right? So I counting rows and j counting columns. So j going from 1 to m, and I is going from 1 to n, right? So when you so this is the main diagonal. At the diagonal, what happened? The column number and row number are the same. Column number, row number are the same. So let's take a general position on the diagonal. So let's say this is the column number j, then which is same with the row number. So on this, at this position, column number and the row number are the same. And now we have to remove these guys, right? So j so your I going from where to where? I going from j plus 1 to n, right? Look at this code. So this is the counter for this is column counter, and I is the row counter, right? And so generally j goes from 1 to m minus 2y, because I consider this this right hand side of the system. So So when you do this we want to yeah, remove these elements. So to do that, if you have number of rows, and let's say number of equations, and number of rows, number of variables are the same, then m and yeah this, so number of rows and number of columns are the same, right? So then this is a square matrix, and the dimension of this one is n by n, right? So with this one and this augmented, what is the dimension of this augmented matrix? Yeah, n by n plus 1. So your m is n plus 1. So we have to remove, yeah, so elements under the diagonal, main diagonal, right? So how many, yeah, so how many columns we have to consider? This one and this one. So if you are considering this matrix, so you have to consider n minus 1 columns, right? Because the last one, so this, if this is a square matrix, so this one, so is this one is located, so if, yeah, this is the last column of the matrix A, and this is located in the last row of the matrix, right? So the m is the number including this row here, this column. So that's why I consider here m minus 2, right? So if you have a coefficient matrix, if A would be a coefficient matrix, yeah, this is m minus 1. If you include your right hand side, then this is m minus 2. Okay, yeah, this is clear, right? Why? When you consider the general j here, and the corresponding index is I is same with j, because this is on the diagonal, right? So we have to remove all elements below this element, so we have to remove these things. So then j, yeah, I index going from j plus 1, j plus 2 up to n, yeah. So you can see, yeah, from here, yeah, so I counting from j plus 1 to n, because we want to remove these elements below this element on the diagonal, right? Yeah, if some of these elements would be, let's assume sum of elements, let's say yeah, let's say one of elements, yeah, under this element is equal to 0, then we don't need to remove this one, because it is already 0. So if this is not equal to 0, we have to, yeah, remove that one. That's why you use this conditional statement. If that element is not equal to 0, then we have to remove that non-zero element, right? So how do you remove this guy here? So first of all, you have to make this guy equal to 1. To make that guy equal to 1, I divide the entire row. This is the row number. So row number is j now, because it, so you know that this is the, so row number and the column number is the same, because this is an diagonal, yeah, this is a diagonal element. So this is in the jth row here. So look at this jth row, right? So right, so this is the entire jth row of A. So I divide the value of that position. So what is the value? So this is the value, right? A of j comma j, yeah, this is the value of A at that point, at that element, right? So you divide entire row by the value of this guy, the value of this guy, right? So j comma j, right? So then this guy becomes 1. This guy becomes 1 when you divide the entire row by this number, right? Then this guy becomes 1. Then what you do, if you want to remove this guy, you multiply this jth row. So this is your jth row now, right? Jth row. So you multiply whole jth row by this by negative of this guy here. So here if you look at the code, I think I made a mistake in the lecture on that day here. So this is the value of this in this position, right? And so you multiply the jth row. So this is your jth row here, this one. So jth row with jth row having this guy equal to 1, right? So you multiply the entire jth row by the negative of this value. So negative here, this is negative of this guy. So then what you do, so then you add this jth row to the this row. You add this jth row after multiplying the jth row by the negative of this value. You add the resultant one to the this one here. So this one here, ith row here, right? So then then the ith row is replaced by the resultant one. So then when you simplify this, what you get, you get 0 here. You do the same for other rows, other elements here, other rows. So then you can make these things equal to 0. So this is this goes up to n number of rows here, this one here, right? So you so sorry. So then from this code, you make this matrix, an upper triangular matrix. So that means, in other words, you remove these all elements under the main diagonal, right, when you execute this code, right? Before discussing back substitution part, let's run this code and see the output. When I compile this, if you go to command prompt, so this is so my file name is test1, and so your a becomes, earlier a would be there's my a, this is my a becomes an upper triangular matrix like this. Here this is the main diagonal. So look at the elements under the main diagonal, everything equal to 0, right? Everything equal to 0, and this is your updated right hand side, and this one is your coefficient matrix. That coefficient matrix has been changed to an upper triangular matrix. So I hope this Gaussian elimination part is clear now. Now let's discuss the back subbing. So how do we obtain solutions to this reduce system? So now this becomes an upper triangular matrix, and B has changed. B has been changed to a new B tilde. Let's say B tilde, right? And you have so variable set, it doesn't change, right? So you know that we start from the bottom, right? So when you find the solution, we find the first yeah from the bottom, right? Yeah, first you have to initiate your variable set. So this is the variable vector, right? It includes how many? Yeah, m minus 1, because here I added, so I added this row. So so if you add this variable vector, you have to add here. So this is your variable vector x. So how many elements are there? The number of rows, columns in matrix A. So how many rows, how many columns are there of matrix A? It has m, so we had to remove by, we had to remove one. So I added this right hand side, you have to remove that number. That's why I here m minus 1, right? I included m minus 1. So it is a column vector with x variable. So I fill that vector with zeros, right? This is the so this is the x sub. So you know that. So this is we start from here. So we start finding x n here. So here let's say this is m here. So xm, right? Or here xm minus 1, right? You know this means, right? This means so then you can compute the last variable, so which is your right hand side. So this is your right hand side of this augmented matrix, right hand side located in mth row. Here we have mth row, right? So and in the mth column, so this is the so this is the sorry, so this is the column number. So the right hand side is located in the mth column, and so this position is the so the last row. So this is the n is the row number and this is the column number. This is your right hand side value at the corner, so at the bottom, this one here. So this one here, this guy, right? So it is divided by the diagonal value of a. So this one here. Then you get the last so x, so last variable. So very last variable, you have the solution for very last variable. Then if you know this one, then we can find x n minus 1, previous variable, right? And if you know these two, then we can find the previous variable of these two. Like that we can find other x i's, right? So for that I use a for loop, right? So this for loop index going from n minus 1 to n, because this is this is going backward direction, right? From the bottom to bottom to the top, right? Okay, so first you find right here. So you know that so in the mth row, in the mth column, you have new right hand side. So right hand side minus and previous so these are so if you look at this here, so you found xm, which is right hand side, this guy divided by the coefficient of this matrix, which is a. So this one, right, this one, and then you can find the previous variable. Yep, so how do you find that? Right hand side, take away, yeah, this coefficient times, yeah, no, this coefficient, the last coefficient times xn, yeah, something like that. So this one is in the on the diagonal, I think. Yep, so yeah, so this one is on the diagonal. Yeah, so here, yeah, this is on the diagonal, right? And this is your right hand side of the equation, ith position of the right hand side, minus, yeah, look at this one. So this is the, yeah, sum of product of yeah, so this is the, yep, yeah, so look at this one, yeah, so it is in ith row, but column number changing from I plus 1 to m minus 1. I think this makes sense why we use m minus 1, right? So in the coefficient matrix, so m is the right hand side, m minus 1. So we know that in the coefficient coefficient matrix there are m minus 1 rows, and including this one, yeah, you have altogether m number of rows and m number of columns, right? So in matrix, A matrix consists of m minus 1 row columns. Yeah, with this one we have m columns, right? So yeah, that's why it is going from, yeah, so I plus 1 to m minus 1. Why this is I plus 1? Because so this position here, j equals I equals j, so you have to get this coefficient value here. So that position is yeah, what is that position? I plus 1. So this is I plus 2 up to m minus 1. So here this is the last one, m minus 1. So a going from I plus 1 to m minus 1, right, multiplied by, so corresponding variables here. So these are the variables. Yep, so you have same index here, right? So right hand side, take away product of yeah, these coefficients with yeah, with yeah, and product of coefficients of a, yeah, going from, yeah, so I plus 1, I plus 2 up to m minus 1. Yep, so this one multiplied by the corresponding x, this one multiplied by corresponding xi, so like this. So then you will get, yeah, when you complete this when this completes this for loop, you get the solution. Let's, yeah, compile this, and let's go to, yeah, so our yeah, command window, and this is your matrix, and this is the solution to that your system. Yeah, this system, this is the original matrix A, and right hand side is this one. Yeah, so yeah, this to this system. Yeah, so this is the solution, and this is the reduce, yeah, this is the echelon form. So this is the reduced, yeah, echelon form, reduce system, yeah. So this is your, oh, yeah, this is the original, yeah. So this is your matrix, coefficient matrix, with the right hand side. So this is the right hand side, and yeah. So when you, yeah, solve this, yeah, yeah, using backward substitution, so you can easily obtain the solution.